We're now going to move on to processing networks of interferograms. You might reasonably ask, why bother doing this when, as we've seen, individual interferograms can tell us about displacement? Processing the interferograms in a network means we can remove some more unwanted effects in the data, which in turn improves precision and allows us to say something about the evolution of displacement over longer periods. This is one way of looking at a network of interferograms. Around the outside are my image dates. There are 16 of them, which is about 6 months of data for TerraSAR-X or Sentinel-1. The lines represent interferograms, and right now I've drawn in every possible interferogram, which is exactly 120 for 16 images. That's a lot of interferograms, and it turns out some of them are not useful. For mining InSAR, the displacement signal is strong, so I don't particularly need all this extra redundancy because the signal readily pokes out way above the noise. Also, the further apart the dates are, the more chance I have of violating my assumption that phase is correlated in time. This assumption actually decays as a function of increasing time, as we'll see in future slides. So instead, I'm going to limit my network where the longest period interferogram is 5 satellite cycles long. So for TerraSAR-X, repeating every 11 days, that's 55 days. This is my pared down network. It contains all the interferograms that are 11, 22, 33, 44 and 55 days long, which gives us 65 interferograms. I can also look at that like this, which makes it more obvious that these interferograms overlap in time. Statisticians or surveyors might accuse this of introducing a false redundancy into the data, and the only real measurements I have are the SAR scenes themselves along the bottom, and creating 65 interferograms doesn't magically create more observations. But as long as you don't skew the statistics, it's fine to do this, and doing so can help with fitting models. Displacement in a 55-day interferogram ought to be 5 times stronger than in an 11-day interferogram, for instance. This is where we left off at the end of the last lecture. We see some likely displacement in the center, but there are still lots of other effects that are likely not displacement. And as a reminder, this is what we're trying to get to. Our final cleaned interferogram showing mostly ground displacement. It's pretty hard to distinguish exactly what's going on here. What we need is an adaptive filter that suppresses noise but enhances areas of higher quality signal. But how do we measure quality in order to make that distinction? We use something called coherence. Coherence is a measure of how well neighboring pixels' phase measurements agree, not just spatially, but in time also. Don't confuse coherence with coherent imaging, in which a fixed wavelength is used. SAR, for instance, is a coherent imaging sensor, but we're talking about something else here, the spatial smoothness of the phase, or the temporal smoothness of the phase, termed coherence. We're going to talk more about coherence later on, but for now take my word for it that it's useful here because once estimated, it tells us how to filter our data. So here's our interferogram before filtering. I'm not going to go into detail about how phase is filtered because it's beyond our scope, but understand that the best filters use the spatio-temporal statistics of largest datasets, say 15 images or more, just like this one. So we're looking at each pixel's neighbors spatially and we're staring through time for each pixel also. And our objective is to enhance the good areas whilst keeping noise as noise. And now here's our filtered interferogram. Notice how immediately more vibrant the data is. Features are crisper and hopefully real noise is still noise. The last thing we want to do is invent displacement. So what's next? Now the data is easier to look at, we can see an odd boundary which demarcates a calmer area in the center and more turbulent data near the edges. This boundary actually represents the extent of the mine's high-resolution elevation data. Their elevation data has done a good job of modeling out the topographic signal at the mine, but outside of that, lower quality open source elevation data has been used to fill in the gaps. In reality, the DEM is far from perfect both inside and outside the mine. Hidden by the displacement we see is likely plenty of elevation error from those mine surfaces, which can change a lot. Also, one might ask, why bother processing areas outside the mine at all? We do this because it helps to zoom out a bit to estimate these wide-scale phenomena such as atmospheric effects, for instance. So how do we fix this residual topographic effect? For most areas, especially those outside the mine, we can consider the effect a constant for each pixel. There is the height that the elevation data tells us, and then there is the reality which the SAR data sees. I have 65 interferograms in my network which all see the same effect, except each of these interferograms has a different B-perp, so the effect is stronger when the B-perp for an interferogram is larger. This difference in B-perp works in our favor though when we're trying to solve for this constant for each pixel. I can in effect write down 65 different equations which all solve for the same constant. So it's a very well conditioned problem, and as long as my data quality is reasonable, it's not a big issue. The process commonly used for this class of problem is called least squares. Perhaps you remember at school trying to eyeball a best fit line through a set of observations, like the graph shown at the top right. Least squares tells you the best place to draw that line. This, by the way, is for any given pixel because different pixels will have different elevation errors. The bottom graph along the x-axis shows the parameter we're trying to solve for, the error in the elevation data. The residual on the y-axis is what's left over, so I'm trying to minimize this residual. If I randomly chose 30 meters as my elevation error, that doesn't fit the data very well. My residual is quite high. The residual is smallest though when I fit a value of 20 meters. Or correcting my pixel by 20 meters makes almost all of the unwanted signal go away in all 65 interferograms. So that's what least squares does. It tells me the solution which minimizes my residuals. I've included the least squares equation here for those interested in the math. Note that this is a weighted least squares solution, and the weights used are my coherence estimates from my filtering step. When I compute a least squares solution for every pixel, this is what I get. This is not an interferogram, it's a map of the solutions to the problem, how much is my DEM in error, for each pixel. And as you might expect, there's lots of correction going on outside of the mine's elevation data. But actually the highest corrections are going on within the mine, which makes sense when we consider pits getting deeper and stockpiles getting higher. The tricky thing about least squares is that this assumes our height error is a constant, but for mined areas it often isn't. Over a 6-month period, the surface heights might change multiple times. So what can we do about this? We could fit a nonlinear solution, but this is way more complicated and has lots more ways of going wrong. So instead, the best and simplest strategy is to simply limit the time period of the fit. I used 6 months of data in this example, but for more dynamic sites, we typically might not go beyond 3 months. Here again is my interferogram before solving for elevation error. When I subtract my elevation correction from it, I get this. The boundary around the mine area has completely gone. Displacement is now the clear dominant signal. Switching back and forth shows how much signal was removed. So this is our finished interferogram. The main leftover contaminant now is residual atmosphere. Happily, most of this cancels out. Without going into too much detail, consider the fact that I have 16 images. Now consider the atmosphere on, say, image 10. The atmospheric influence of image 10 has a kind of negative effect for the interferogram made from images 9 to 10, but a positive effect in the interferogram made from images 10 to 11. And the net effect for the atmospheric influence from image number 10 on the results is therefore 0, because it cancels out, barring some process noise. So the only atmospheres that don't cancel out from my stack of images are those that occurred on the first and last dates, because they have nothing to cancel with. This summarizes the network or multi-temporal processing efforts. In the top row, we used the spatio-temporal statistics of the data to determine which areas have good signal and which areas are noise. These quality estimates are called coherences. More on coherence in the next lecture. We then use least squares to solve for a correction to the elevation data. That's in the middle row. And the final step, which I haven't mentioned yet, is to take all of my shortest duration interferograms, 11 days in this case, and convert their phase values to something like centimeters or inches, and use them directly to make displacement time series for each pixel. I can also easily compute things like a displacement rate layer, shown in the bottom right, or make a map of which areas are accelerating, for instance. Here's what a displacement rate heat map might look like, with a time series shown for some pixel. This might either be a result from a single pass, say just ascending images, so it tells us the one-dimensional line of sight displacement along that look direction. A more complex analysis, though, combines results from 2 or more different passes to improve coverage and provide more information about the direction of displacement. We're going to talk more about displacement results in a future lecture, including the benefits of combining ascending and descending results. For completeness, I want to mention how straightforward the conversion from phase to displacement is. My displacement in centimeters or inches if preferred equals the phase in radians multiplied by the wavelength over 4 pi. Why 4 pi? Normally angles to distance conversions would involve dividing by 2 pi, but remember we need to account for our signal's round trip from the satellite to the Earth and back again. Otherwise we will double count our displacement. So when we plug in the numbers for a single fringe of displacement, so 360 degrees of phase or 2 pi radians, which is 6.28 radians, and we use the TerraSAR X wavelength of 3.1 centimeters, we get 1.5 centimeters of displacement. So one fringe for TerraSAR X is 1.5 centimeters of displacement.